Hello, this time level 1 of the frequency response questions. Let's get a question. Right, now we have 4 different alternatives to choose from, but again the circuit is a simple low-pass RC filter, and we could work out the pole frequency of that. That would just be 1 divided by 2 times pi times r times c. That would give us about 23.4K. Right, so we're looking for a response which goes down by 3 dB at 23.4 kilohertz. So that looks like it could be either A or D. Now, there's only one pole here in this frequency response, so we'd be looking for a curve which goes down at 20 dBs per decade. And just looking at it, A is going down by about 20 dBs per decade, from minus 12 to minus 32. D, however, is going down from minus 18 to minus 56 or so. That's much more than 20 dBs in this decade, so D must be the result of having 2 poles, not just one, each pole providing a 20 dB per decade roll-off. So the answer must be A. Next. Right, here we've got a problem that looks very much like a level 0 problem, just an RC circuit wired up as a high-pass filter. At high frequencies, the signal would go straight from A to X because a capacitor at high frequencies just looks like a short circuit. At low frequencies, none of the signal would get from A to X because it would all be blocked by a capacitor, which at low frequencies looks like an open circuit. Anyway, the pole frequency we can calculate from the time constant, and the time constant here is just RC, so that'd be 47 times 680 nanofarads, about 32 microseconds. And to calculate the pole frequency in hertz, we would take 1 over the time constant and then divide by 2 pi to get the answer in hertz. Fine. Next. Okay, we have another low-pass filter. At high frequencies, they're going to be shorted to ground through this capacitor, so it cannot be B. It must be A or D or C. Which one? Well, let's work out the pole frequency again. The pole frequency is 1 divided by the time constant, which is 330 times 6 mu 8, divided by 2, and then divided by pi, about 70 hertz. So if I look around here at about 70 hertz, I can see that it's A that's dropped by about 3 dB at 70 hertz. So A. Here we have one which we've got to look a little more carefully about. Let's see. We can't see this curve actually getting to its final asymptote level, but it's going to be at approximately this level here, which is 85.6 dB. And where are we 3 dB down on 85.4 dB? And that would be about 82.4 dB. So go down here until we find 82.4 dB. There. That is the frequency at which we are 3 dB down on what looks like approximately the final value. And that's 2.6 kilohertz. That's probably close enough. Yes, it is. Great. Another very simple one, just like level 0. Should know how to do these by now. 220 times 15 micro divided by 2 divided by pi. Fine. And another one here with 4 to choose from. This time we have an inductor. Now, at very high frequencies, inductors have very large impedances. At very low frequencies, inductors have very low impedances. So we would expect there to be very little loss at all at low frequencies. And all of these waveforms have that characteristic. We would expect them to have a much higher loss at higher frequencies. And all of the waveforms have that characteristic. So, have to look a little more carefully. Where is the pole frequency here? Well, For a LR, an inductor resistor combination like this, the pole frequency in radians per second is given by the resistor divided by the inductor. So that would be 1500 divided by 10 milli. And that's in radians per second, so we'd have to divide by 2 and divide by pi to get the answer in hertz. So around about 24 kilohertz we'd be looking at. And 24 kilohertz is about here. C is about 3 dB down at about 24 kilohertz. All of the others are much, much further down at the pole frequency, so the answer must be C. If I'd calculated the pole frequency and found it was around about here, I would have to look at the gradients of these slopes and notice that A is dropping by about 20 dBs per decade, whereas B and D are both dropping at around 40 dBs per decade. Well, if there's only one pole, and here we only have one pole, since there is only one reactive element, the answer must have been A in that case. But here, it's C. What frequency would this circuit have its pole? Well, 1 divided by the time constant, divided by 2 divided by pi. And another one of these, another LR low-pass filter. So it cannot be B, but it could be C, A, or D. Here we can instantly tell that it must be C, because C is dropping from minus 16 to minus around 36, about 20 dBs in 1 decade of frequency, from 100 kilohertz to 1 megahertz, whereas both A and D are dropping faster than that. Their gradient is greater. If you've only got one pole here, which we do, the answer must be C. A and D are dropping too fast. They must be the result of circuits with more than one pole. So the answer here, C. Save a bit of time. Don't have to work out the pole frequency if there's only one possible correct answer on the curve. Right, I think that's about enough.